Well, I must admit I'm addicted. I'm addicted to making these videos. So I'm doing a fourth video on the same day. 4 videos in one day, but I love it. It really is fun. All of these videos are spontaneous, unplanned, and still they are scientifically correct. And well, I assume that you are interested in computer science and possibly you want to be a computer programmer. Maybe you are already a programmer or have some experience in programming and want to know the scientific background a bit better. And well, this is the reason why I decided to make this lecture about one of the core concepts of computer science, which is important for programming, and this is the concept of the algorithm. So what is an algorithm? Or what is a computer program? We are programming. What is a program? So obviously a program is something we create as programmers, and what is our job? We want to make the computer do something, what we want. So a program is more or less a set of instructions that tell the computer to do something. And an algorithm, well, this is a term that is a bit more scientific, and let me put it this way. A program can be an algorithm, but usually it is parts of the programs that are considered algorithms. And there are also programs which are, in scientific terms, not algorithms themselves. And the reason for this is that algorithms have to terminate. So a program doesn't have to terminate, it can also end up in an endless loop. But an algorithm has to terminate. And to understand this better, we must think of a bit of mathematics. In mathematics, we have mathematic functions. So a function is kind of a black box into which we throw some values and then we get a result. And so, let's say the function of x is 3x plus 2. So if we throw the value 16 into it, 3 times 16 is 48, plus 2 is 50. So this is the result which the function returns. And an algorithm is actually the way a computer is programmed in order to process a mathematical function. So that is what an algorithm is all about. If we have a mathematical function, then this function actually can be recursive. This is also a topic that is somewhat famous in computer science. A function can itself contain references to other functions. So instead of function of x being 3x plus 2, it could also be 3 times a function g of x and this plus 2. And then g of x could be defined as something different, for example 4x plus 16 or something more complicated. Anyway, you notice that in this case you can compute this, if you compute it the traditional way, by first inserting the definition of the function, by substituting the function symbol with the definition of the function. And then, in the next step, you substitute whatever symbols appear in the definition of the function with what they should be. So, for instance, first you substitute f of x by 3g of x plus 2, and then in the next step you substitute g of x. And this actually is a way of programming which is called functional programming. So there are some computer languages, for example Haskell or Scala, which either are functional languages or allow you to do functional programming. And in functional programming, it's really like this, that you define functions like you do in mathematics. So, and these functions can themselves have references to other functions. So, and the computer language that the compiler that processes this computer language, or usually it is an interpreter in this case, so it is a program that takes the instructions and processes them from the source code, from the code written in a programming language, while a compiler first translates the code from the programming language to the universal machine language. And the interpreter doesn't do it, it processes it at runtime. So an interpreter, this is what processes it at runtime, would in a functional programming language start by substituting the symbol of the function, and then if again there are symbols of other functions, it substitutes, and only once everything is substituted and we only have primitive operators and variables and all of this, then it calculates the result. So the result of a function, actually, it is a mathematical value. You can have a parameter, it can have many parameters, several parameters actually, which are variables, and you can pass values, and you get a return value. This is functional programming. And usually a program actually is not only about calculating something. So a program may be using of functions, and these functions have algorithms that produce the result. But the program actually usually does something. For example, it outputs something on the screen. Think of a computer game. A computer game is something that shows action on screen. It displays characters. And so if you want to create a computer game, then you cannot just calculate a mathematical function, but you have instructions that have side effects on the screen. So basically, this way of functional programming is somewhat unnatural, and it is something a bit novel, because the traditional way of programming is imperative programming. And imperative programming means that you command the computer to do something, that you have instructions that tell the computer to do something, and the program is processed instruction after instruction. And an algorithm itself can be created in several fashions. It can be created in a functional fashion or an imperative fashion, for example. There are famous algorithms, like for example the sorting algorithm quicksort, which can be written as a functional program or as an imperative program. There are these several ways of writing this algorithm are logically equivalent. They produce the same result for the same parameters. But the notation is different. And, well, it may even be that the way the program works, if you say take a look at the instruction by instruction level, is slightly different from when you compare a functional program with an imperative program. So the algorithm is how a computer computes a mathematical function. And programs can be algorithms themselves, but they need not be, because programs need not terminate. Algorithms have to terminate. And usually we have several algorithms used by one program, and we use these algorithms to achieve certain things. And one of the things that is often cited when we are talking about algorithms is sorting algorithms, the problem of sorting a numerical sequence. So for example, let's say we have 4, 6, 2, 1 or something like this. So this should be sorted into 1, 2, 4, 6 in ascending order. So the first values which I said, I think it was 4, 6, 2, 1, this would be the value of the parameter, the input parameter, and the output would be 1, 2, 4, 6. And so how is this achieved? This is achieved by the algorithm. And if we remain at this example, sorting, I mean, the first thing I had in mind when thinking about sorting was that I would just look at all of the values and select the smallest one and mark it as selected and take it, and then take a look at the other values, mark again the smallest one, mark it as selected, take it. And this can actually also be done by simply replacing the first value in the sequence with the one you selected, the smallest one, and swapping the places of the two numbers. So that the number which previously was the first one appears somewhat later in the sequence. And because this is about selecting something, this is called selection sort. And a different way is insertion sort. And insertion sort means you start with the first number, you compare it with the second number. If they are in the wrong order, you exchange the places. And so on, you continue until the number that was previously the first number has found the correct place. And then you start with the second number, and so on. And this actually also works, and this is called insertion sort. And these are two quite simple sorting algorithms which are somewhat intuitive. So most people, when they are completely new to this topic and then confronted with this, come up with one of these algorithms. And these algorithms work, but they are not efficient. And this is the reason why are they not efficient. This is simply because they take a lot of time. And the time is measured by the size of the input data. So if the input data, let's say, is n, n being some natural number, usually it is measured in bit, so in binary digits. So this is just a unit. Then you can say that some of this, for example, selection sort has an average runtime of n to the power of 2. So this is quite non-efficient. And there's also this algorithm bubble sort, which is not efficient either, which is about, well, you compare the first number with the second number. If they are in the same order, then in the right order you keep them, otherwise you swap them, and you compare the second with the third, and so on. And when you have reached the last two digits, then, or numbers, then you check if you did at least one swap during the the traversing of the sequence. And if you did, then you traverse the sequence again from the start. And well, you do it until no exchange has happened. So this is also an algorithm that works but is inefficient. And an algorithm that is far more efficient, for example, is quicksort, or also merge sort is an efficient algorithm. Quicksort having the advantage that it's an internal sorting algorithm, so that means that you do not need to allocate additional memory, at least not the same number of memory bits as the input size is, because you don't have an input and an output, but but you modify the input, and then you output the input, the modified input. And this is possible with quicksort, while merge sort actually is already an external sorting algorithm. Also, it is sometimes more efficient than quicksort. It is faster, and it also takes more space, more memory. So the take-home message is that an algorithm should terminate, while a program does not have to terminate. An algorithm computes a mathematical function, and you can write it in several styles, functional programming, for example, or imperative programming, and that there are several algorithms which solve the same problem, but they are different in efficiency. So this is what I have not said yet. So the science of algorithmics is about finding the most efficient algorithm, or at least an algorithm as efficient as possible for solving a particular problem. And there's also the term complexity. So this complexity can be the runtime complexity, or it can also be the memory complexity. In any case, it shows you how efficient an algorithm is. So the less complex, the better. And complexity theory actually is also a really huge field of computer science. And the P&P problem, for example, is a problem of complexity theory. So at least it is something that has kept generations of computer sciences occupied, and it is still unsolved, and maybe it isn't solvable at all. Yeah. Okay, I think that's enough for now. So I hope you learned something, and maybe you enjoyed this lecture. So see you.